All right, L'Hopital's rule. So what is this? Unit 15. It's definitely not day 3. It's more like lesson 3. Again, final new notes for the year. You're probably not done learning though, right? Like you'll still learn some things, but this is the last new day of notes. L'Hopital is more about, like, the process is easy, but the format is harder than the process, I guess. And that's usually not true in math. Usually, as long as you can get to the right answer and show some work, fine. But for L'Hopital, I guess we'll just phrase it, the format matters. I'm trying to think of a better word than format. Like how you show your work matters. We'll talk about it in a minute. But the process is pretty easy, but you got to make sure you do it the right way to get credit on the AP test, basically, for next year. Or, no, this wouldn't be on the PreCal AP test. So, format matters. All right. Evaluate this limit or show that the limit does not exist. So, if I plug in -2, I get 0 over 0. But that's not allowed. I don't know what that is. So, do you remember how we would do this one? What we would do? Let's factor the bottom. Plus 2, and then I'm thinking about same, opposite, always, positive. Square the first one, multiply the 2 together, square the second one. Factoring a cube. But the reason we did that is the x plus 2's will cancel. And now we can try substitution again. So 1 over 4 plus 4 plus 4, also known as 1/12. Okay, so we did that limit with some algebra tricks, an algebra method, factoring. Number 2, if we plug in pi, 1 plus cosine of pi over sine of pi. Cosine of pi is -1. Sine of pi is 0. We can't have 0 over 0. So, do you remember how we fixed this one? What algebra trick we would use? We will eventually use sine squared plus cosine squared equals 1. But what do I have to do before I get to that? The conjugate, which is 1 minus. Top and bottom, 1 minus cosine of x. So the top becomes 1 minus cosine squared. The bottom, don't really do much with the bottom, just leave it. Sine of x times 1 minus cosine of x. And then now we use, you guys were saying sine squared plus cosine squared equals 1. So I need to rearrange that to get 1 minus cosine squared. Sine squared, this one's easy. I didn't have any signs to worry about. S-I-G-N-S, signs to worry about. So if I move the cosine over, I get sine squared. And then one of the signs will cancel. And then we try again with our substitution. So sine of pi over 1 minus cosine of pi. 0 over 1 minus -1. So 1 plus 1, so 2. And 0 over 2, that's fine. That's just 0. 0 over 0 we didn't know, but now we've got 0 over 2. Okay, so not great, not horrible though, like the algebra methods. And if you get 0 over 0, you're probably at a hole in the graph. I mean, you're certainly at a hole in the graph if you have factors that cancel. for sure. And so here were our algebra tricks. We could factor and reduce. We did that. That was number one. We multiply the complex fraction. We didn't do one of those just now. And multiply by a conjugate. That was number two from earlier. So those are our algebra rules that we use. You can laugh. It's okay. But now we're going to add another option for evaluating limits. Another option for evaluating limits. Now, it's a great option. It's an easy option. But it can only be used, so here's the key. Like some people learn shortcuts and they like apply the shortcut to like everything. You're like, well, wait a minute. You can only use this rule if your limit results in 0 over 0, infinity over infinity, or negative infinity over negative infinity. Those are called indeterminate, meaning we don't really know, like what's 0 over 0 equal to. Sometimes it's 0, sometimes it's undefined, sometimes it's infinity, sometimes it's 3, like we don't know. So if you substitute and you get one of those, then you can use L'Hopital rule. So if f and g are both continuous functions, and they yield 0 over 0, or infinity over infinity, or negative infinity over negative infinity, meaning something you can't deal with, then here's the rule. So there's our original limit that we couldn't get, or we didn't know. Limit as x approaches a of f over g. So if you get one of these indeterminate forms, then what this also equals, the limit as x approaches a of f prime of x over g prime of x. So all you have to do is take the derivative of the top and derivative of the bottom and try again. And usually it's a pretty simple derivative, because this is not the quotient rule, right? This is not gf prime minus fg prime over g squared. You're not taking the derivative of the whole thing. You're taking the derivative of the top and the derivative of the bottom separately. And sometimes this gets confusing because students will do one of two things. They'll either use the quotient rule for L'Hopital, which wouldn't be right, or they'll try to use like L'Hopital when they should be using the quotient rule. So if it's a limit, you can use L'Hopital. The L's go together. Limits, L'Hopitals, that's when it's easy. Just derivative top, derivative of the bottom. And there's a picture of this derivative. I don't know if he's related to hospitals or not. That's a good question. Somebody should Google that. Guillaume L'Hopital. Okay, so let's try this and see how this works. Number one, evaluate that limit or show that it doesn't exist. The other thing is you can't jump straight to L'Hopital. You have to show that you get 0 over 0 or infinity over infinity before you use the trick. So if I plug in 5, let's see, that would get me 25 minus 15 minus 10 over 25 minus 25. So yeah, that is not going to work. Okay, here comes the format issue. In order to use L'Hopital, you have to state that the top limit is 0 and the bottom limit is 0. Like this little shorthand is not enough. You have to, it's annoying, you're not going to like it, but you have to take the time to write out each individual, like the top is 0. And the bottom is 0. So if the top is 0 and the bottom is 0, then we can use L'Hopitals. So we're going to say therefore, and we can abbreviate a little bit here. Therefore, L'Hopitals. So limit as x approaches 5, and now we can do the derivative. Nice when they're easy derivatives. So 2x minus 3 in the top and 2x in the bottom. Again, not quotient rule, just derivative of top, derivative of bottom. Try again with the substitution. 2 times 5 minus 3 over 2 times 5. So that would be 7/10. Super convenient, usually easier than any of the other algebra tricks we used. And so students are like, yeah, this is easy. Again, the main thing though is you've got to have this statement in there on a free response question. On a free response question, you must say or show that each, let's phrase it this way, the numerator and denominator, not demon, denominator, equals 0.
Yes, Mr. Wolf, do you know if there's going to be, sorry, John, can I cut you off? Do you know if there should be free response in the test?
I'm pretty sure there will be, just so we can test this specifically. Jonathan? What's that?
The acid not in his name in French.
Okay. Is he related to the hospital thing, or did you? No? Okay. Okay, so I'm thinking there will be a free response portion of the test specifically to test this, that you state that the top limit is 0 and the bottom limit is 0, therefore use L'Hopital, and then you can jump to the shortcut. So I guess that's the price you pay for taking the shortcut, is you got to show a little bit of work. It's not hard work, but you have to state it or show it. Number 2, evaluate that limit or show that it doesn't exist. Again, you always have to check to see if substitution works. Although this is on the L'Hopital worksheet, so I'm pretty sure we're going to get 0 over 0. So let's jump to showing them separately here. So there's the top limit. So if I plug in 1, pi x, but if I plug in 1, cosine of pi is -1 plus 1 is 0. And the bottom, if I plug in 1, I get 3 minus 1 minus 2, so that's 0. So if the top is 0 and the bottom is 0, then we're eligible to use L'Hopital. Therefore, L'Hopital. So let's take a derivative of the top. Derivative of cosine is negative sine. But that's not all. What else do I need?
Not chain rule.
Not quotient rule, chain rule, yes. So chain rule gives me times pi, because I have to take the derivative of pi x. And then derivative of the bottom, 6x minus 1. So let's plug in -1. So negative sine of, not -1, we're plugging in 1. So negative sine of pi times pi over 6 minus 1. Sine of pi is 0, so 0 over 5 equals 0. Again, we like L'Hopital, but you've got to state the top equals 0 and the bottom equals 0. Number 3. Let's see, if I plug in 0, I get 1 minus 1 is 0. I guess it's okay to do it kind of shorthand. Natural log of 1 is 0. So I do get 0 over 0, but that's not what we're looking for. That's not enough to say use L'Hopital. I mean, it's enough for you to know to use L'Hopital. It's not enough to get the credit for using L'Hopital. So limit as x approaches 0 of the top e to the 0 is 1. Minus 0 minus 1 is 0. We already know we're going to get 0 for both, but we have to show that. Limit as x approaches 0, natural log x plus 1. Natural log of 1 is 0. Again, this is like the annoying part of L'Hopital, is the upfront work. The nice part of L'Hopital is, therefore, we can use L'Hopitals, take a derivative, and have something easier to work with, assuming we can take derivatives. So derivative of e to the 2x would be e to the 2x times 2. Derivative of minus 5x would be minus 5. And then in the bottom, we're going to get fractions and fractions, but that's okay, we can deal with that. 1 over x plus 1. Chain rule, like we got to consider it. It doesn't add anything here because we would be multiplying by 1. So the derivative of x plus 1 is 1. Okay, well now let's plug in 0. It is a fraction within a fraction, so you might want to fix that first. But I think we should plug in first and see if, see if it doesn't just take care of itself.
Mr. Wolf, why is the derivative of e to the 2x to e to 2x?
Because the derivative of e to the orange triangle is e to the orange triangle, but chain rule times the derivative of the orange triangle, which was 2. Some people like the orange triangle stuff. Some people are like, why are we taking derivatives of orange triangles? Well, trying to show the chain rule. So e to the 2x stays the same, but derivative of 2x is where the 2 comes from. All right, let's plug in 0. So 2 e to the 0 minus 5 over 1 over 0 plus 1. So 2 minus 5 is negative 3. 1 over 1 is 1. And so, yes, we had a fraction and a fraction, but it worked out to be relatively easy. Yep. Number 4. I plug in 0. Pretty sure I know what's going to happen. 1 minus 1 is 0. 0 squared is 0. So let's try L'Hopitals. Or let's show that the top is 0 and the bottom is 0, and then we'll use L'Hopitals. Again, this is sort of the annoying part of the problem, because I already know it's 0 over 0, so I'm going to use L'Hopitals, but I've got to show this step, this statement, that the top is 0 and the bottom is 0. Okay, now you're unlocked access to L'Hopital by showing that. Okay, derivative of 1 minus cosine. Well, derivative of 1 goes away. Derivative of cosine is negative sign, but the two negatives make a positive. Sine of x. Derivative of x squared is 2x. So let's plug in. Sine of 0, 0. 2 times 0, 0. Uh-oh. Be very careful here. Do not write equals 0 over 0, because it does not equal 0 over 0. I don't know what it equals yet, but it does not equal 0 over 0. So if you put 0 over 0, that's fine. Even if you put equals, that's fine. But then you better mark it out and say, whoops, I can't get 0 over 0. What do we do if we get a limit that's 0 over 0? Do it again. And that means we get to make the statements again. Limit as x goes to 0 of sine of x equals 0. And limit as x goes to 0 of 2x equals 0. Therefore, we get to use L'Hopitals again. It's just going to get worse all day. It's funny now. Wait till 6th period. Okay, so I'm looking at this guy and taking another derivative here. Derivative of sine is cosine. Derivative of 2x is 2. And now we plug in 0. Cosine of 0 is 1. 1/2. Why is that different than what Miss Murray has? Oh, because she made a mistake. That's why it's different. Or whatever. Once in a while it happens. Kind of a funny anecdote down here. My voice is going, so I'm not going to read it out loud, but I encourage you to read that just for your own enjoyment. Bernoulli kind of got cheated out of a rule, although he has his own equation he probably used in physics, or at least heard of. Yeah, Bernoulli's law, Bernoulli's equation, Bernoulli's principle. So he did get credit for that. Maybe he wasn't working for L'Hopital at the time. Number 5. Okay. If I plug in infinity over infinity, or if I plug in infinity, I get infinity over infinity. So I can use L'Hopital. And, I know why I like number 5. Number 5 is a multiple choice question, meaning I'm only looking for the answer. Meaning I don't care. I mean, I do care about your work, but you don't have to write out the full thing. So you're just going to say, I mean, you might not even write this, but L'Hopital means 10x plus 7 over 4 minus 14x. We plug in again. This time we get infinity over negative infinity. So we can L'Hopital one more time. 10 over negative 14, which is negative 5/7. There is a different way to do that one. Do you remember the rule? If you have x going to infinity, that's when you can do top no, bottom O equal co. But L'Hopital is pretty easy, so meh, either one, whichever you like. They both get you there. All right, number 6. X cubed over e to the x. Infinity over infinity, so L'Hopital's, so 3x squared over e to the x. That's still infinity over infinity, but like we're getting closer to something, so let's L'Hopital again. 6x over e to the x. I'm still at infinity over infinity, so L'Hopital one more time. I should at least label what I'm doing. L'Hopital. Now if I plug in infinity, I get 6 divided by e to the infinity, also known as 0, because you're doing 6 divided by something really, really big, which is really, really small. It never equals 0, but again, this is limit, so we're approaching 0. Okay, the next section, some of you are going to like a lot because it doesn't require a whole lot of work. But some of you are not going to like it a lot. You're going to dislike it a lot because it requires a little bit of thought. If the limit of f over g results in infinity over infinity, then we kind of have to ask which infinity is bigger, which infinity is more infinity than the other infinity. It's which one is stronger, which one gets bigger faster. So here's our list of things that get bigger faster. X to the x, like that blows up super fast because x is getting bigger and the exponent's getting bigger. So like that's super strong. Like that's the highest you could get. X factorial, that would be big for kind of the same reason, because you'd still have x factors being multiplied, but it's less than x to the x, because x to the x, like once you get to 1,000, that's 1,000 thousands, but x factorial is 1,000 but stepping down, so this is a little bit less. Next down the list would be something like e to the x, or 2 to the x, or 3 to the x. Again, think about when x gets to 1,000. That's 1,000 threes. That's a lot, but that's a whole lot less than 1,000 times 999 times 998 times 997. So 1,000 threes is big, but less than factorial. Down from there would be x, x squared, x cubed, like powers of x, square root of x. Because if x is 1,000, you're not multiplying 1,000 things. Maybe you're squaring 1,000 or cubing 1,000, but that's still way less than any of the others. And then at the bottom of the strength chart here is logs. Like especially think about the graph of a log. Like yes, it's increasing, but it is not increasing very fast. As opposed to e to the x, which is blowing up pretty quick, but not as quick as the others. So you can either memorize that, or maybe you can think through it each time and figure out which one is bigger. So number 7. If I plug in infinity, I get infinity over infinity, but which one of those is the bigger infinity? Natural log or x squared? X squared. I mean, you could, again, think about the graph. You know that natural log increases, but not really that much. So x squared is a stronger infinity. I don't know if that's the best way to say that. A stronger function. It gets bigger faster. So what's my answer then? If the bottom's getting bigger faster than the top, 0. Number 8. Again, infinity over infinity. And think about, like, I mean, yes, the table's over there, but if I plugged in 1,000, the top would be 1,000 times 999 times 998 times 997 ... E to the 1,000 would be, E a bunch of times. So which one's bigger, the top or the bottom? The top. Because like they both would have 1,000 factors, but the top factors are way bigger than the bottom factors. So if the top is way bigger, way stronger than the bottom, what are we headed toward here? Infinity. Number 9, sine of x. Sine of x wasn't on our list. What does sine of x do? Show me with your hand what sine of x does. Oh, you're thinking unit circle. That was it just looks like this. So it's always between -1 and 1. And natural log of x is getting bigger. Here's some very fancy official math for you. The top is between -1 and 1. The bottom's getting bigger, bigger, bigger. So what are we headed toward? 0, because we're dividing by a bigger and bigger and bigger number. And the top isn't getting any bigger. It's oscillating. Okay, tangent of x. Ooh, tangent of x wasn't on our list, but let's see, tangent of x is x goes to 0. It's like that. Yeah, I don't think I'm going to figure this one out just by thinking about it. Let's plug it in. 0 minus 0 over 0. So I think we got a L'Hopital situation here. Derivative of tangent is secant squared. So secant squared x minus 1 over 3x squared. If I plug in 0, let's see, secant of 0, the cosine of 0 is 1. I flip that over, I get, and then if I square that, I get, so what am I going to have to do now? Again. So back to this guy, L'Hopital on him. Oh, derivative of secant squared. Yuck. Well, the derivative of secant is secant tangent. But before I get to that, I've got to think about power rule. So 2 times secant of x. And then the derivative of secant of x is secant tangent. At least the 1 goes away. I got that going for me. All over 6x. Yep, if I plug in 0, I definitely have 0 in the bottom. And tangent of 0 is 0. I'm going to have to do it again. Before I do it again, it would probably be helpful to make this secant squared. And now I've got product rule. I think this will be the last time I have to do a derivative because the bottom's going to give me 6. So I'm definitely not going to get 0 over 0 anymore. So the bottom is 6. The numerator is going to be awful. So I'm going to go first times derivative of the second. So 2 secant squared x. Derivative of the second, derivative of tangent is secant squared. Plus, the other way around, so tangent times derivative of the first. So bring the 2 down, so 4 secant of x times secant x tangent x. Sorry, what's that? One like this? Probably. See, I think I did that right. So, double check here. That's first times derivative of the second plus second times derivative of the first. Now, there is good news coming because I know 6 is in the bottom, so we're good there. What's the tangent of 0? 0. So this whole second term, which means even if I had messed up some of that stuff, as long as the tangent showed up in there somewhere, it was going to wipe it out. So I don't have to worry about that. 2 secant fourth, which I guess sounds terrible, but we already said the secant of 0 is 1, because the cosine of 0 is 1. We flip it over, we get 1. We raise it to the fourth, we're still at 1. 2/6, aka 1/3. Blah. So how many times did we do L'Hopital there? Once, twice, 3 times. And then we had to use product rule and chain rule and trig and all of the things. Yuck. Alright, today's assignment is worksheet 4. Thursday, aka tomorrow, is a quiz. The quiz does not have L'Hopital on it. Okay, the quiz does not have any L'Hopital stuff. It is all worksheet 1 through 3. Alright, that was your last new pre-cal lesson. We ended with a bang and a voice crack.
Like and subscribe.
Like and subscribe, especially to this one. That's right. You don't want to miss any future cracking videos.